Hello students, let's resume our discussion on graphical description. We talked about 3.1 and completed. Now let's talk about by far the most important topic here in section 3, histograms. What is a histogram? Here's an example. We begin with something called frequency table, and let's consider the same data set. An exam score distribution, and if we use stem and leaf display, we get something like this. Let's see, let me expand the font a little bit here. One student in 30s, no student in 40s, one student in 50s, 4 students in 60s, 10 students in 70s. Can you see all these? Now, you can create something called class intervals and then put those in interval expression like this. Between 30 and 40, between 40 and 50, between 50 and 60, between 70 and 80, kind of like this. But there's a rule, very, very important rule. Semi-inequality to the left and strictly inequality to the right. Semi-inequality to the left, strictly inequality to the right. And think about this. If you scored precisely 80, what's your grade? You graded B, not C. If you scored precisely 90, you earned an A. That's not a B score. If I give you B precisely at 90, then you have legitimate reason to complain. Now, if I give you B after 89.6, then yeah, you're going to complain me, but only to a certain degree. Okay, if you scored something like 89.6, probably I'll give you an A, but theoretically at least. So that's how you can understand. So semi-inequality to the left, strictly inequality to the right. If you scored precisely 70, then you don't belong here. This is D. You belong here at C. All right? And then you count the number of students, the frequency. Or you can calculate the relative frequency by dividing by total. And this kind of thing is called a frequency table. And that's closely related to stem and leaf display if, big if you have class interval goes for unit of 10, as you see here. Now, based upon this frequency table, you can produce a histogram, and the histogram looks like this. A standard histogram. Let's run it, and let's copy and paste this picture here. Okay. Compare this picture with this frequency table. One student in 40 to 50. One student in 30 to 40 right here. And nobody in 40 to 50. So nothing here. Or there's a rectangle, but it has height 0. And one student in 50 to 60 goes up to 1. And 4 students in 60 to 70. So this rectangle goes up to 4. Make sense? Horizontally, we have to have class intervals. Vertically, we have frequency. That's a histogram. That's why it is related to the frequency table. Or you can use relative frequency if you want. Instead of going up to 10, we have 10 out of 23 and 6 out of 23 and so on. So if you have exactly the same shape, but the labels here will differ. Instead of going from 0 to 10, you're going to get 0.2, 4 point something. Either way, that's called a histogram. But unlike the stem and leaf display, which is tied to tens, you have a little bit more flexibility with frequency table and histogram. Instead of going over to, the threshold of 10, let's suppose you are in a little bit more generous mode, and then you're curving your grade so that you're going to 12.5, for example. the second picture, green picture. Here we go. 87.5 or higher is A this time. So we have 2 A students. And 75 to 87.5 is B. Now you have 12 B students. And then 62.5 to 75 is C. So you have 7 students there. And 50 to 62.5 is D. You have 1 student. That didn't change. No, that did change. That's D. Sorry about that. That's D. A, B, C, D. And then only 1 F student. Okay. Makes sense? So this one had a direct connection to the stem and leaf display, but you can generalize like this. That flexibility is one of many advantages of histograms. And of course, you can produce frequency table based upon the new histogram instead of going from 90 to 100, 87.5 to 100, 75 to 87.5. You can reproduce that. I'm going to leave that to you. And then here's the third attempt. This time, I'm going for class interval size of 7.5. So, and like this. Things are a bit different. Each width is 7.5 this time. This kind of flexibility gives us advantage on histograms. So this is by far the most important graphical presentation for us. And that is the standard histogram. By the way, please note this trait. Same class interval width. Okay? Horizontally class interval, vertically frequency or relative frequency, but same class interval width. And rectangles touch each other unless there's a gap of nobody in this class interval. Or there's a rectangle, but the height is 0, so you can't see. Touching each other is not that important of a distinction. I mean, that it's not really that important of a characteristic of a histogram. But class interval here, that's important. Frequency or relative frequency here, that's another important thing. And also, finally, we have same class interval width everywhere. And I used to tell my students in Math 1680, Elementary Probability and Statistics class, that use same class interval size unless you know what you're doing. That's what I say. If you use uneven class interval size and you make a mess, then of course I take off points, or actually I give no score as a matter of fact, 0 out of 10. I grade really harshly there because that's one of the common mistakes, but it seriously undermines all kind of research methods everywhere. If your initial class interval decision is like that, then afterward everything else fails. So I grade rather harshly there. And then I tell them, do not use uneven class interval width unless you know what you're doing. Now this is 3000 level maths course. So what I say is, you must know what you're doing. Okay? You must know what you're doing. You should be able to deal with uneven class interval width too at this level. So what's the conclusion? Well, same class interval, same data set, this time uneven class interval width, and one student out of 30 and 50, and one student in 50 to 60, and one student from 60 to 65, the same height proportional to the frequency. Does this look right? One student here in this big interval is equally as important as one student in this little interval. Doesn't make much sense, does it? This one makes more sense. This one is correctly done advanced histogram with uneven class interval width. How? Class interval width is proportional to area, not the height, area. That's the real trait. You see, you should know what you're doing. It's 3000 level course, so everybody should know what you're doing. And the key here is frequency or relative frequency is proportional to the area of each rectangle. Now, if the width of those rectangles are all the same, then area and height are proportional. And that's why we had an illusion that you can use height for frequency or relative frequency. But that's so 1000 level or high school level. Here in 3000 level, let's get out of there. Let's completely discard the notion of height because that's not correct anymore. Let's focus upon the area, and it happens that areas and height are proportional when we have the same class interval width. When we have uneven class interval width, you have to go for area. And area, does it ring a bell? It's calculus. You see, area of a rectangle, hey, we are talking about Riemann sums. Eventually, it's going to become definite integral. And it becomes kind of like this. Height of the rectangle is basically frequency over class interval width, because you see area is frequency or relative frequency. So area is height times width. So you see, height is going to be frequency over class interval width. You see? Make sense? Area is height times width. And that's... oh, never mind. Let me just put one more here. Over... okay. Area is width times height. So if I divide area over width, then you're going to get height. Alright? And the area is frequency. So we have what? Frequency over interval width. But then again, interval width, well, that's delta x, difference of x coordinate. Well, here's a picture. You see, x coordinate here. So that's delta x. And then frequency can be rewritten as, now this is the tricky part, the difference of cumulative frequency. Does it make sense? You see, if you keep adding up frequency, then you're going to get cumulative frequency. So if you subtract, then you're going to get frequency. This may be a little bit difficult to understand, but it turns out like this. So what do you have? Delta, the difference of cumulative frequency over delta x. And if I name this cumulative frequency as capital F, then delta capital F of delta x, hey, we have a derivative. Indeed. Indeed. Alright. Even though calculus 1 was prerequisite, I think I got a bit too much here. So let's stop here. Let's not get overboard here. Don't get carried away. So, okay, let's make a summary. Advanced histogram. Area corresponds to, relative frequency or frequency corresponds to area. That's important, remember. The key point is the area. Alright? We got an illusion that it's okay to use height because we were using the same class interval width. The real key was the area. Remember that? And the area is associated to calculus, especially the fundamental theorem of calculus. So we are going to be using some calculus later on, and that's where I'm going to stop. As for that delta f over delta x kind of thing, I think I got a little bit carried away. You can forget about it for the time being at least. Alright, so much for histograms, and the next topic is the OGIF. And the OGIF is like this. We have class interval size and frequency, and we can consider cumulative frequency. Cumulative, what do you mean by that? Keep adding up. Do you remember we talked about cumulative frequencies for Pareto diagrams? And did I say it's a stepping stone? Yes, indeed. So, from 30 to 40, there's one student. So that's cumulative frequency of 1. Nobody was added, so staying 1. and then 1 student from 50 to 60. So cumulative frequency from 30 to 60, or from 0 to 60 is now 2. 4 students from 60 to 70. So I'm adding 4. So from 0 to 70, I have 6 students. Okay? This is cumulative. And then 10 students in 70 to 80. So I'm adding that 10. So from 0 to 80, I have 16 students. Remember, this is cumulative. Add them all up, and I get a total of 23. That's called cumulative frequency. And then an OGIF is kind of like Pareto diagram, histogram plus this line graph of cumulative frequency put together. Here we go. So here we use frequency. Start from 0 because nothing was added, and then the first rectangle of 1 student, and stay as 1 because nothing was added, nobody here, and then 1 more student, so it became 2, and then 4 more students, and then 10 more students. So keep increasing because this is cumulative frequency. Start from 0 and end up at total. This thing is OGIF. So OGIF is related to cumulative frequency, and down here we have the histogram. Another way to do that is to use the relative frequency. Instead of from 0 to 100, or excuse me, 0 to 23, we have 0 to 1. And then we have relative frequency here, and I'm using advanced histogram here. So uneven class interval width. So here I have only 5 students, class interval of 5. Here I have class interval of 10. Here I have class interval of 10, kind of like this. It doesn't matter. Cumulative relative frequency. So I keep adding up. Eventually I stop at 1. So we have an OGIF, the red line graph, and then we have a histogram, the pink rectangles put together. Histogram and OGIF. In conclusion, OGIFs give you cumulative frequency. Wait a minute. In conclusion, okay, the calculus thing again. I guess I got a bit carried away. Alright. Never mind, it's a bit too deep here. Basically, the derivative OGIF corresponds to histogram more or less. And that's something we will end up coming back and studying in a little bit more detail. That is, the derivative of cumulative distribution function tends to be the probability density function. And this is the descriptive statistic version of it. Something we have to come back and study at, let's see, I think around module 6 or module 7, I think. Week 6 or week 7. Okay, so much for all those concepts, and let's have a brief discussion on example problem. The following table shows a monthly electricity use of a certain household, and of course, this is my bill. Okay, and that produces a histogram and an OGIF. Well, I didn't specify what kind of class interval width do you want to take, so you can do it freely. And whatever class interval you take, and then just count the numbers and produce those. But let me discuss a wrong solution first, because when I wrote this problem in 2014 and to an elementary class in 1580 class, I'm afraid every single student there produced a picture like this and got 0 score. This is not a histogram. The width, class interval width, no, I don't see class interval here. They are just months. Frequency, these are not frequencies, these are electricity use. So this is not a histogram, just a bar graph, but everybody did it this way and got score 0. That's why I wanted to show you this. Here's an example of a frequency table and a histogram, and then an OGIF. Well, that's about it.